Here I present a simple but powerful little principle. I call it the little engine that could. Start with a shuffled deck of cards. Okay. Have the spectator shuffle them if you would like. Okay. When you're done with that, what we need is 2 piles of 26 each. You can have the spectator do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. So if I know how to count, we should have 2 packets of 26 cards each. Okay? Very good. So what I need you to do is, so I'm speaking to you as the spectator. I need you to choose either pile, okay, as yours, and the other one would be mine. Which one would you like? This one, right there? Okay. And now I need you to choose a color, red or black. You like red? Okay, very good. So what I need you to do is go through here and count the number of red cards in your packet, okay? And it's okay if I see it, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Very good. So you have 14 red cards in your half. Okay? So what I need you to do now is just simply set my little packet of cards on top of yours. Okay? Just like that. Okay? So I want to make a prediction here. So you had 14 red cards. 14 red cards. Well, I think the 14 is going to allow us to find perhaps the most popular card in the entire deck. And you may know what that is. It's the Ace of Spades. So what I need you to do is count down 14 black cards from the top. Okay, so let's go ahead and do that together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wow. 12, 13. So the next black card I predicted will be the Ace of Spades. So let's see if I'm right. I was indeed. You found the most popular card among all 52 cards, and that was from a shuffled deck. How in the world did you do that? Okay, so that is called the color of thought. Okay, color of thought. It may come in many different names for all I know, but that is one name that I've come across for this little effect. The color of thought. Okay, so it is based on, as I mentioned, a little principle that carries quite a punch. And it's not a principle that's too difficult to wrap your mind around. And because of that, this is a little principle you can take with you the rest of your life. And using a shuffled deck of cards, you can accomplish some really fun, surprising things with the spectator. Okay, so let's talk about what in the world is going on here. How were we able to do that? Okay, so first, let's talk about, now there's no name that I am aware of for this principle that I'm going to present. So I came up with a name. It seems like a reasonable name. I call it the equal opposite parts principle. And you'll see why that name is apropos here in just a second. So given a dichotomous packet, so dichotomous just means to split into two, like red, black, yes, no, on, off, that kind of thing. Okay, so given a dichotomous packet of, say, red cards and black cards, if it is divided in half, which is what we did, then each half will contain the same number of cards of one color as the other half contains of the other color. So what that means relative to red and black cards, which is really what we took advantage of here, is we know that in a deck of cards, there are 26 red cards and 26 black cards. Okay, so the deck is evenly divided by color. Okay, so that's a prerequisite here. And then the claim is, this is the claim, that if you divide, now this won't be a perfect division, I'll just estimate. Let's say there's 26 there, 26 there. No matter how you divide a standard deck of cards, we are guaranteed to have the same number of red cards in this half as we have black cards in this half, okay? And vice versa. Now, if in your mind's eye you can see, oh, of course that's true, then that's wonderful for you. You'll have an easier time remembering this principle and making use of it. But not everyone can immediately see that that has to be true, okay? So why don't we just take a moment and look at a visual justification for why this is true. Now, this principle can be confirmed using some fairly laborious algebra. And I'll even point you to a video where that's done if you want to see all of the algebraic steps that could be gone through to confirm the truth of this principle here. But I think with this graphic that I've drawn over here, for 99% of people, this will be sufficient to convince them of the truth of what this principle is claiming. Okay, so what I have here is I have a circle. Now, the circle represents all 52 playing cards. All 52 playing cards are somewhere in here, okay? Now, we have this division, that's the red line, natural division of half of the cards being red and half of them being black down below, okay? So these are all red up here and these are all black here, okay? Now, this bluish line here is denoting a random division of the deck into two equal halves, okay? So what that means is you can just draw a line through the center of the circle out to the boundary of the circle, okay? Now, look at what happens. So I have this line cutting right through the center and then attached on opposite ends of the circle, okay? Well, just think through this. This is representing all of the cards in this half of 26 cards. And down here, this is representing all of the cards in this other half of the deck of 52 cards. Okay? Can you see what happens? And we can just see it by symmetry here. So no matter where this line is drawn, we're going to get the following consequences. The number of black cards. Okay, so let's focus on the upper left kind of diagonal portion here of this division. Okay, over here, we're going to focus on those cards. Okay, now most of these are red up here, right? These are all red cards, okay? And then we have this little slice of black down here, okay? Now, what's going to happen by symmetry is we're going to get a similar division of the bottom half of this portion of this circle where we will get this equal, congruent little piece of red cards, which perfectly match the number of black cards in this upper portion of the deck, okay? And the same thing for the red cards in this upper division of the deck will exactly match the number of black cards in this lower division of the deck. Okay? So if you just draw a diagram like this, you'll save yourself a tremendous amount of work writing it out algebraically. Now, it's a good exercise to write things out algebraically to confirm that, yes, indeed, it is true, okay? But I think this is an intuitive result that can be understood with a relatively simple diagram as drawn here. So this shows the conclusion of the principle. So no matter where this division is made into two equal halves for the deck of cards, it will always be the case that the number of red cards in one division will have to match the number of black cards in the other division of the deck, and the number of black cards in that first division of the deck will have to be equal to the number of red cards in the other half of the division of the deck. Okay? So anyway, that's a graphical confirmation that that principle is indeed true. Now, let's go ahead and kind of explain that. That doesn't fully explain at all, actually, what we just did with the color of thought. It truly is the engine driving it, but you would have to kind of connect some dots still to be able to show that that little principle is behind this effect that we have just demonstrated. Okay? So let's think about it here. So we have a deck of 52 cards, half are red, half are black. Okay, so if we divide this in half, what's going to be the case? Okay, so once again, I'm just kind of estimating, but we could divide exactly, but okay, so what's going to be the case? Well, let's go back to what you did. You chose this portion and you chose red. Now, the number of red cards in here will match the number of black cards in here, okay? So the number of black cards here matches the number of red cards that you counted out. Well, what does that actually mean? Okay, so the number of black cards here matches the number of red cards that you'll count out. Well, a consequence of that is the following. The bottommost black card, now which happens to be a king of spades, will be in the position determined by the number of red cards here, right? So think about it. Let's say you say there are 14 red cards in here. Well, that means there's 14 black cards in here. Well, what that means then is as we count down these, 1, 2, and so forth, when we get to the 14th black card, well, we know what the last black card is in this half of the deck. It's staring at us. It's the king of spades, okay? Now, it is true that if we didn't have a black card at the very bottom, we would have to play detective a little bit more, right? Because we would have to know what is the bottommost black card in this packet. Okay, bottommost meaning the lowest. Well, it's the king of spades still, right? So it was just serendipity in the case of my performance that right half happened to have an ace of spades at the bottom that I was able to glance as I was moving the packets around, okay? So what's really happening here is the number of red cards here matches the number of black cards here. And if you know the identity of the bottommost black card, then you can state with certainty that whatever the number of red cards are, if you count down that number of black cards, you'll arrive at the one that you glimpsed, the one that you noted, okay? So that really is kind of the engine driving it and kind of a clever use of the fact that we know that these packets have the same quantity of cards, but of the opposite color. So same number of red as blacks here, same number of blacks as reds here. Okay, so that's the principle itself and a fairly simple application of the principle. I just have a couple of notes here. What you can do a little differently, I did this one here. So let me just show you both of these really fast. Okay, so let's say we split the deck in half, okay? And like I said, just pretend that there are 26 and 26 there. And the spectator this time chooses this one. Why don't we turn it like this? This is their half, okay? This is mine. And let's say they choose black as their color. So what we're going to do, we're going to have them count the quantity of black cards in their half of the deck. So how many black cards are there? Okay. And really, you could actually have them quietly do that if you like. There's a bit of danger in that because they could either lie about the quantity of black cards and throws off everything, of course, or maybe make a mistake. So I don't think it's bad for you to kind of see and watch them count out all of the black cards. Now, once they've done that, and assuming that you know the bottommost red card, okay, so we can see what it is here. It's a 3 of diamonds. Okay, so really the only information you need to know regarding this half is what is the bottommost red card? Well, that bottommost red card will be arrived at if you count down the number of cards they just counted for the black cards in their half. Okay, so how I did it was I put mine. See, remember, this is what they're going to count down to. This is the one I'm going to say, I think you're going to arrive at the 3 of diamonds, I believe. Okay. So look at what happens. If I put this here, well, maybe let's back up. Look what happens if I don't put it there for now. Okay. So what's going to happen is they will, let's say there's 16 black cards here that they've counted. Well, that means there's 16 red cards here. Well, they're going to go through 1, 2, 3, 4, and then the very last card in this half will be the 16th red card. Okay. Now, I suppose for some spectators that may not be giving away too much information, but I suspect it will, because it's like, okay, how did it come out to be the last red one? I wonder if the number of black, this is the spectator kind of puzzling it through, and you don't want them to necessarily, right? They're going to think, oh, I wonder if the number of black cards here is the same as the number of red cards here, because you've essentially blown your cover is what you've done. So to avoid that, the technique I've come up with is you just put yours as a performer, your packet on top of the spectators. Now remember, the spectators counted how many black cards are in their half. And you've noted your 3 of hearts at the bottom. It's the bottommost red card. So what you do is you set it on top of their half. Well, what does that do? Well, it just hides things, right? Because now if they go, let's say, what did I say, 16 black cards in their half or something. So you're going through here and counting how many red cards there are. 1, 2, 3, 4, 5. You get all the way up to 16, and that 16th card is guaranteed to be the 3 of diamonds. Well, it's most likely they're not keeping track of, not really doing that right here. They're not keeping track of how many cards total, right, that they've dealt. So you've kind of buried the position of that special card, the 3 of diamonds, back in the deck, okay? And so as they're dealing them off, very few people would go, I wonder how many cards are here, and then count them off and go, oh, that's 26. I wonder, that's interesting. Okay, so that's one way to hide it. Another way to hide it, which is not my idea. It comes from the original presentation that I came across of this color of thought, is what you do is, let's go back. Let's say we have two halves here. So we have two equal halves, and they've counted the number of black cards. And we know that the bottommost red card, when we even just put one on the bottom, just for clarity, this time it's the Queen of Diamonds. So maybe they say there's 12 black cards here. Well, we know that the 12th red card from the top will be this Queen of Diamonds. Well, what you can do differently is you just do this countdown tuck. Now, I made that up because I don't know if there's a name for this otherwise. So what you do is you go through and have them keep a running count of the number of red. Okay. So you go, so that's one, the 0, right? 0, 1, 2. So we're just counting the reds, right? 2. Finding any red, 3. So anyway, you go through until you get to that 12th red card, and it will be the card that you noted. Here, it would be the Queen of Diamonds that we just showed you. Okay, so what's happening here is you're kind of losing that card deeply within this sort of convoluted process of noting the red, putting them back underneath, okay? So it's like you're going in circles. Well, no one's going to be counting how many times you've done this, okay? So the fact that your special card is in the position that equals the number of black cards here won't be detected at all. Okay, so anyway, that's just a kind of a simple application of this principle. Now, I do want to point out there's some other obvious divisions that you can use for this. Of course, we have an equal number of red and black. You could have a little packet that has the 12 face cards and then 12 numbered cards. In that principle, this equal opposite parts principle will still apply. Interestingly enough, the even value number cards and the odd value number cards, if you include the ace as 1, right? There's an identical number of those two groups of cards. There's 20 of each. We have 2, 4, 6, 8, 10, and then ace, 3, 5, 7, 9. And there's 20 of each of those. Okay, so we have this kind of dichotomous packet there, perfectly divided into evens and odds. So this principle can be used. Okay, so there's many other divisions that you can think of, right? You could have the clubs and the hearts as like one half, and then the spades and the diamonds as the other half. That would be a perfect kind of division of the deck. Okay, for our second application of the equal opposite parts principle, I call it reds equal black. So what we're going to do here is I've started with a shuffled deck. It truly is shuffled. Doesn't matter what order these cards are in. And so if it's red, I'm going to put it on the left and then place a card below it face down. If it's black, I'm going to put it on the right with one card face down below it, okay? So we're going to go through and do this for all of the cards in the deck, okay? Now, you may want to think about, is there anything that we'll know about these bottom down facing piles? So think back to the principle that we just kind of introduced. And is there anything you can conclude by using that principle regarding the composition of reds and blacks in these down facing piles? So kind of ponder that as I do the work of dealing these, okay? So how would you apply it here? Okay, almost there. A couple more. There we go. Okay, here. So we have two piles in this column. So we have a pile of up-facing red cards, of course, and then a pile of just down-facing cards. We're not sure what's in those cards. as far as reds and blacks. And then we have this pile of black cards on the right with a corresponding down-facing pile below it. Is there anything that we know that might be kind of fun to, reveal? Well, it ends up, and it's kind of hard to believe, really, is that the number of red cards here must be equal to the number of black cards here. Okay? So that is not a direct consequence of the principle that we showed you. Because the principle that we showed you is that if you have equal portions of reds and blacks in a packet, divide those in two, then that conclusion follows. There'll be the same number of red in one pile versus black in the other. But the fact is, there's different numbers of cards in these two piles. Okay? So that's not the way in which this principle is or can be applied, actually, because we have more cards here than we have here. Okay? That will not allow us to use that principle. Okay? That principle simply will not apply. Okay? But nonetheless, how can we know? So there's a number of ways that you could actually take advantage of this information. Now we haven't proved it yet, but you could simply just state, believe it or not, you shuffled those in just the right way so that over here, the number of red cards will match the number of black cards. I don't know how you did that, but that's got to be a 1 in a million outcome. Okay. Well, in reality, it happens every single time. But why don't we go ahead and just show you that it's actually true, right? We haven't actually shown you. So how many red cards do we have? 2, 3, 4, 5, 6. Okay. There's 6 red cards. I'm going to put it like that so it fits on the paper. So the claim is there's going to be 6 black cards over here. 1, 2, 3, 4, 5, 6. Okay. And that will always happen. Okay. Well, let me show you a proof of this. So we're going to do the following. We already know that the number of cards in this pile and this one must be the same because that's how we created them. For each red card we set down, we set a face down card down. Okay. The same thing here. For each card dealt here, we have a card down below it. So why don't we say there's n cards in this pile? So we have n red up-facing cards. Well, that means we also have n cards there. We'll just call it n down-facing cards. Now over here, we have a different number of cards. We'll call it m. And they're black up-facing cards. Well, these two piles also have the same number of cards in them. So we can say this one is a pile of M cards, and they're all down-facing. Well, what do we know? We know that the total of all of the cards is 52. So, for example, we can write 2n plus 2m is equal to 52. Well, we can divide both sides of this equation by 2. So we would get n plus m is equal to 26. This is all we really need to know to complete this proof. And then we'll use our equal opposite parts principle. Okay, so how can this one equation help us draw the conclusion that we need to? Namely, that the number of red cards in here is equal to the number of black cards in here. Well, just look. If we take these cards right here, so in your mind's eye, go ahead and add those. We'll do a little plus. Add those to these. So combine all of those. combine these cards with those cards. In fact, why don't we physically do that? We'll kind of move the cards around. So I'm going to take these N cards and I'm going to move them next to the M cards right here, right? And then I'm going to do a similar thing. I'm going to now take these M cards and put them next to the N red up cards, like this. Okay? Well, what do we know? We know that the sum of these two packets is 26. That's how they were gathered. We know that the sum of cards in these two piles combined will also be 26. So these constitute a perfect division of a deck of cards into two halves right now. Okay? Well, what do we know? So we know that the number of black cards here this is like 26 cards, must be equal to the number of red cards for this second half of the deck. Okay? But just look at this. The number of black cards in this half will be completely determined by the number of black cards in here. Right? Because there's no black cards in here. These are all red. So we can say the number of black cards in this packet, because there's none there, must be equal to the number of red cards in this packet because these are all black. Right? Okay, these don't contribute any red cards. So from there we can conclude that the number of black cards in this packet must indeed match the number of red cards in this packet. And then if you just remember where we got these from, this one came from over here, right? We just do our little reversal here of where we took them from. And so now we can say that the number of red cards here is equal to the number of black cards there, okay? And we didn't need really any more than two variables to represent what's going on here. And really, in your mind's eye, you could have actually just done that without having to write down anything, really. Because if these two piles are equal, and these two piles are equal, then it's just as I've written here. It's like having N, N, M, M. Well, you can go ahead and take this one with this one, you'll get half the deck. This one with this one, you'll get half the deck. And then you just draw the conclusion that I have. Okay, well, anyway, that is the principle kind of explained for why there would be the same number of red cards in the one pile where you've dealt out one for one, a card for each red up-facing card, as the number of black cards in the other pile where you've dealt out one for one, a down-facing card for each up-facing black. Okay, very good. Now, the other idea is called the free exchange principle. And what you need for this is you simply need a structure where you have two packets of cards, and you can have different numbers of cards here. But if you know that the number of red cards here matches the number of black cards here, then a one-for-one exchange will not upset that equality. Okay? So why don't we go ahead and just kind of step through a simple explanation for that. So why don't we have 5 red and 5 black over here. And then the number of black here don't really matter, and the number of red here won't matter for what we're going to do. Oh, we don't want the same number. Okay, so let me just show you what's going on with this principle here. Okay, so what it's saying then is if, maybe I'll move this kind of off to one side so I can use some of the space here. Okay, so here's one packet. Okay, so here is a kind of a simple example of it. Now the packet sizes here don't have to be the same, right? So I have 7 here and then I have 8 here, okay? Now, what we're claiming is if this packet, let's say, has the same number of red cards, 1, 2, 3, 4, 5, as the number of black cards in the other packet, 1, 2, 3, 4, 5, then when you exchange a card 1 for 1, it will not change that equality. Okay, so let's just see that for ourselves here. So let's say somebody wants to exchange this one right here, the red. Okay, well, think about this. If they exchange it for a red here, it doesn't change anything. Everything's exactly the same in terms of how many reds and blacks are on each, right? But if they exchange it for a black, what's going to happen? The number of black cards here will decrease by 1. And the number of red cards here will also decrease by 1 because you just lost that 1. Okay? So if you think about it, the number of red here, if they match the number of black here, it doesn't matter how you exchange these, that equality will remain. Okay, I'm going to show you an original application of the equal opposite parts principle. Okay, so I have a shuffled deck here, and it truly is mixed up. Maybe I'll give it one more shuffle here. Okay, now instead of putting out colors, I'm going to put out suits. Okay, so here's a diamond, and I'll put one below it. Another diamond, very good. A heart, a club, a spade, perfect. Okay, and then we're just going to repeat this. So for each suit I put down, I just set a second card down below it. Okay, so similar to what we were doing before, but there it was just for red and black cards. But now we're looking at all 4 suits. Well, if you understand the previous principle with the reds and blacks being equal in quantity, you should be able to anticipate what's going to happen here. And most likely your intuition is going to be right. Okay, so we have 4 piles and of unknown sizes. We really don't, we could not know ahead of time how many cards are in each of these. Okay, it will very much depend on the state of the deck before we started doing the dealing. It really will. Okay, so we get this. Sorry, I'm just being OCD here, bumping things all over the place. Okay, very good. And so after doing this, I would just have the spectator choose any 2 suits. Any 2 suits whatsoever. Okay, and so let's say they choose clubs and diamonds. Okay, so those are theirs. So what I would have them do is go ahead and gather up clubs. So maybe I'll turn them sideways. So this is their little pile. They're going to gather those, and diamonds. Okay, that's for the spectator. That leaves me these 2, hearts and spades. Those will be mine. Okay, now there's a few ways to proceed here, actually, now that you know the free exchange principle. So let me kind of tell you the punchline, and the punchline could actually be the effect itself, if you like. But regardless of the suits they choose, if you now combine those cards, like they chose these 2 little piles. So if we combine them and mix them and so forth, and I do the same for mine, 2 little piles, it ends up that they and their little packet of cards will have the same number of clubs and diamonds added together as I will have hearts and spades in my packet added together. Okay, so why don't we actually just check that? I mean, that may actually be a little hard to believe. So, so here we go. I'm going to move those up here just to give us a bit more space. So here is, okay, I'm going to put it sideways, if that's okay. Just trying to show everything on the camera. Okay, so here are the, we're looking under the hood here as to what's inside each of these little packets. Okay, we'll kind of see what's going on here. Okay, and then we'll come over here, and then this is the last one, and maybe we'll put it like that. Okay, and looks like everything fit fairly. Okay, so my claim is that if they chose clubs and diamonds, so the far ends of things, the number of clubs and or diamonds in these two will equal the number of hearts and spades in here. So why don't we go through, we're going to count up how many clubs or diamonds are in this packet. So this is part of their, so they would actually have these two combined, right, together. So they'd go through here and go, okay, I'm looking for a club or a diamond. So one diamond, so I have two, 1, 2, come over here. Oh, here's a club. 3, 4, 5, 6. That's it. So they would have a total of 6 clubs and or diamonds, right? They have a total of 6 clubs or diamonds in their portion of the deck. Does that match the number of hearts or spades that I have? Well, let's go ahead and count them. So I'm looking for hearts or spades. Okay, so there's a heart, 1. There's a spade, 2. Here's a heart, 3. There's a spade, 4. Another spade, 5, 6. Okay, so that matches. We had 6 clubs or diamonds in this portion of the deck, and then we had 6 hearts or spades in this portion of the deck. Okay, so they would have actually kind of gathered their cards together. This would have been their pile. They would have left me these, and then you can state with certainty the conclusion, right? The number of hearts and spades in there will have to match the number of clubs and diamonds in here. Okay, and so you may want to think through, okay, how could we arrive at that conclusion based on the earlier work that we've done? And I don't think it will be too hard for you to see how that can be accomplished, actually. It really is just an extension of the principle that we've been looking at. Okay, now, from here, though, from here you can actually now move in to a free exchange little routine. How's that? Well, the spectator is chosen as their 2 suits, clubs and diamonds. So maybe what we'll do is, well, why don't we go ahead and do that? I'm going to put this over here to remind us. Those are those, the spectator suits are those 2. And then that left us with these 2 suits. So I'm just going to move all these cards out of the way. We actually don't need them anymore. Okay, so these are my suits and these are their suits. Okay. And so now we're going to, we wouldn't show each other our cards, of course. And what will happen is, regardless of how many cards are exchanged for each other between these 2 hands, the number of clubs and diamonds here will be equal to the number of hearts and spades here. So in some ways, I think that really ramps up the impossibility of the whole thing. I mean, that's starting to get just mind-blowingly amazing, okay? Because you have to realize we started with a shuffled deck. We dealt out piles according to the suit, and then we dealt a down-facing card for each suit, that up-facing suit that was dealt, fine. but that was arrived at randomly because the deck was randomly shuffled. The spectator then is free to choose any two suits as theirs. And then by default, the other two suits will be yours as the performer. And from there, we give them the down-facing cards that are paired with the clubs and the down-facing cards that are paired with the diamonds. That becomes their new special packet. And we get the down-facing packets that are associated with the hearts and spades. And then, unbelievably, we are now allowed to exchange as many cards between ourselves as we like. And none of that will change the fact that in the end, the number of clubs and diamonds here in the spectator's hand will exactly match the number of hearts and spades in ours. In fact, why don't we I'm just going to grab a bunch of things. I'm going to grab the top three just to show you here. And maybe we'll do the bottom three here. We'll do a little switch just to kind of show you this exchange principle. Now, I really encourage you to try this on your own, and you'll see, man, this works, okay? And then maybe review the proof of it that I showed you for the original simpler case of just reds and blacks. Well, it extends readily to this situation here of four suits. Okay, so what are we claiming? We're claiming that now the number of clubs and diamonds in here, that total will match the number of hearts and spades over here. So why don't we go ahead and count them? Okay, so we're looking for clubs and diamonds. That's what the spectator would be counting. So they would go, 1, 2, 3, 4, 5, 6, 7. Okay, so they would write down 7. I have 7 total of clubs and diamonds. Okay, and then you would count yours. So, but what you're looking for are hearts and spades. So you would have 1, 2, 3, 4, 5, 6, 7. That's the last one. There's 7. It's the final one there. You got 7 as well. You both got 7. And the equality of those two quantities is invariant under this exchange procedure. You can exchange as many cards as you like, which is unbelievable, I think, and would never be detected by anyone watching this. Okay? And really, unless you delve into the mathematics of all of it, you really won't know. You will have no clue as to how in the world is that possible? No clue. Okay, so anyway, that's an original effect using this powerful little principle. That's why I call it the little engine that could.